Somewhere inside a room the size of a tennis court, a single machine focuses light so precisely that it can etch patterns onto silicon smaller than a virus. That machine costs more than most private jets. It takes several cargo planes and dozens of trucks just to move one from the factory to the customer. And once it arrives, it takes months of specialized engineers working around the clock just to assemble it inside a clean room built specifically to receive it. Every advanced chip powering the phone in your pocket, the servers running artificial intelligence, or the processors inside the fastest computers on Earth exists only because a company most people have never heard of figured out how to build this machine at all. The company is ASML. It doesn't make chips, it doesn't design phones, laptops, or graphics cards. What it makes is the machine that makes the machines that make everything else possible. And understanding why that machine is so hard to replace tells you more about the modern economy than almost any other single company could. To understand why ASML matters, you first have to understand what a chip actually is, at the most basic physical level. A modern processor is built from billions of microscopic switches called transistors, packed onto a sliver of silicon a few centimeters wide. The more transistors you can fit into that space, the faster and more powerful the chip becomes, and the less energy it needs to do the same amount of work. For decades, the entire semiconductor industry has been engaged in one relentless project, making those transistors smaller, so more of them fit into the same tiny area. This project even has a name most people have heard of without necessarily knowing what it describes: the expectation that the number of transistors on a chip would roughly double every couple of years. That expectation only held for as long as engineers kept finding ways to print smaller and smaller features onto silicon. The moment that stopped being possible, the entire trajectory of modern computing would stall. But you can't just carve transistors into silicon with a knife. You print them using light. This process is called photolithography, and it works something like an extremely precise stencil. A pattern is designed on a template called a photomask. Light is shone through that mask, and a lens focuses the resulting pattern down onto a silicon wafer coated in a light-sensitive material. Wherever the light hits, a chemical reaction marks out the pattern that will eventually become the wiring and structure of the chip. Do this layer after layer, dozens of times, aligning each new pattern with total precision on top of the last one, and you end up with a finished chip containing billions of transistors stacked in dozens of interlocking layers, thinner than a strand of hair. For decades, this process worked using deep ultraviolet light, and for a long time, it worked well. Engineers kept finding ways to squeeze more performance out of the same basic idea: sharper lenses, more accurate motion systems, better chemistry on the wafer surface. But underneath all of that incremental progress sat a hard physical limit that no amount of clever engineering could fully escape. Light has a wavelength, and there's a fundamental flaw to how small a feature you can print using light of a given wavelength. It's the same reason you can't paint a fine detail with a fat brush. At some point, the tool itself becomes bigger than the thing you're trying to make, no matter how skilled the hand holding it. As chip designers pushed transistors to be smaller and smaller, they ran directly into this wall. The deep ultraviolet light being used to print the patterns was physically too coarse to draw features that small with acceptable precision. For years, the industry got around this limit with increasingly elaborate tricks. One breakthrough involved submerging the final lens in a thin layer of water. Because light bends slightly differently traveling through water than through air, and that tiny shift in behavior was enough to squeeze out a meaningful improvement in resolution. Another trick involved splitting a single chip layer into multiple separate exposures, printing part of the pattern, then printing the rest in a second, carefully aligned pass, effectively doubling or tripling the work needed to produce one layer of the chip. These techniques worked, and they kept the industry moving forward for longer than many engineers originally expected. But they were expensive, slow, and increasingly fragile. Chipmakers weren't printing one pattern per layer anymore. The most advanced layers needed to be exposed 3 or 4 times just to hold together at all. The cost and complexity of manufacturing were climbing sharply with every new generation. and it was only a matter of time before this patchwork of workarounds collapsed under its own complexity. The obvious solution, at least on paper, was to abandon deep ultraviolet light entirely and switch to a dramatically shorter wavelength. Shorter wavelength means finer precision, the same logic as switching from a fat brush to a fine-tipped pen. The specific wavelength engineers targeted is called extreme ultraviolet light, or EUV, sitting at roughly 1/14 the wavelength of the light being used before it. On paper, it solved the wavelength problem cleanly. In practice, it created one of the hardest engineering problems the electronics industry had ever attempted to solve, and it took roughly 3 decades, multiple companies across several countries, and tens of billions of dollars in combined investment to get from the idea to a machine that could reliably run inside a factory. The first problem was simply generating the light in the first place. Extreme ultraviolet light doesn't exist in any convenient, controllable form in nature. You can't just switch on an EUV light bulb, and no existing laser could produce it directly. The method that eventually worked, after years of failed alternatives, involves firing a high-powered laser at microscopic droplets of molten tin, tens of thousands of times per second, vaporizing each droplet into a plasma that emits EUV light for an instant. Each droplet is a few dozen micrometers wide, smaller than a grain of flour, and the laser has to hit each one twice in rapid succession. First to flatten it into a disc shape so it presents more surface area, then to blast it into plasma at exactly the right instant, with the timing accurate to fractions of a millionth of a second. This has to happen continuously, tens of thousands of times every second, hour after hour, for the machine to generate a usable, stable beam of light at all. Early prototypes of this light source were so unreliable and produced so little usable light that for years, many engineers inside the industry seriously doubted EUV would ever become commercially viable. There are stories, well known inside the industry, of entire development timelines slipping by years because the light source alone kept failing to hit the brightness and reliability targets needed for a real factory. The second problem was even stranger, and in some ways harder to solve. Extreme ultraviolet light is absorbed by almost everything, including ordinary air. A beam of EUV light, traveling through normal atmosphere, loses nearly all of its energy within a short distance, which meant the entire optical path inside the machine, from the light source, through every mirror, all the way to the silicon wafer, had to sit inside a near-total vacuum, engineered to a level of cleanliness closer to a space telescope than a factory tool. And because EUV light is absorbed by ordinary glass as well, engineers couldn't use conventional lenses to focus or direct it, the way every previous generation of lithography machine had. Instead, the machine relies entirely on mirrors, coated with dozens of ultra-thin alternating layers of different materials, only a few atoms thick, engineered so precisely that if a single mirror were scaled up to the size of Germany, its surface bumps would still be smaller than a millimeter tall. Multiple of these mirrors bounce the EUV beam through the machine in sequence, and each mirror absorbs a portion of the light's energy along the way. So by the time the beam reaches the wafer, only a small fraction of the original light survives, which is exactly why the light source has to be so extraordinarily powerful in the first place, just to leave enough usable light at the very end of the journey. Every part of the system has to compensate for that loss without introducing any distortion, because the final pattern printed on the chip has to align with the layers printed before it at a precision measured in a handful of nanometers, on a wafer moving beneath the beam at high speed. None of this was solved by one team in one lab on one timeline. This is the part of the story that explains why ASML's position is so difficult to challenge, and it has almost nothing to do with a single patent or a single clever trick. Building a working EUV lithography system required assembling an entire network of specialized suppliers spread across multiple countries, each solving one piece of an almost impossibly difficult puzzle, and integrating their work into a single functioning machine that could survive daily use inside a live factory. The mirrors and lenses at the heart of the system come from Zeiss, the German optics company, whose engineers spent decades perfecting mirror polishing and coating techniques accurate enough for EUV. Building on optical expertise the company had accumulated over more than a century in completely different fields. The laser system that vaporizes the tin droplets was developed by Cymer, an American company that ASML eventually acquired outright, precisely because the light source had become such a critical bottleneck that ASML judged it too important to leave in the hands of an independent supplier it didn't fully control. Other components. Precision motion stages that have to position a silicon wafer with sub-nanometer accuracy while moving it at high speed, vacuum systems capable of maintaining an almost perfect void around the optical path, cooling systems that manage heat generated by components operating at the edge of their physical limits, and control software capable of coordinating thousands of variables in real time, adjusting constantly for vibration, temperature drift, and material fatigue. Come from a wider network of specialized firms, many of which exist almost entirely to serve this one supply chain and few others. This is the point where it becomes important to be precise about what ASML actually does, because it's easy to overstate. ASML did not invent every technology inside an EUV machine, and it doesn't manufacture every critical component itself. What ASML did was something arguably harder to copy than any single technical breakthrough. It acted as the systems integrator, the one organization capable of coordinating dozens of world-class specialists in optics, lasers, precision mechanics, vacuum engineering, and software toward a single functioning, reliable machine, and doing so consistently enough to sell that machine to customers who needed it to run continuously at scale for years. Inside a live factory, producing chips worth billions of dollars a month. That distinction matters, because it explains why a competitor cannot simply reverse engineer an EUV machine by studying a diagram of it. Even with complete blueprints in hand, a rival would still need Zeiss-level optics manufacturing refined over generations. A tin plasma light source perfected through years of iterative failure, precision motion engineering built on decades of earlier, simpler machines that came before it, and critically, the accumulated operational knowledge of what actually goes wrong when you try to run this system continuously in a real chip fab 24 hours a day, for years on end. That kind of knowledge isn't written down in a patent filing. It exists inside the heads of engineers who have spent careers on this one problem, inside decades of failure logs nobody outside the company ever sees, and inside working relationships between ASML, its suppliers, and its customers that were built through years of joint problem-solving under enormous financial pressure. It's worth pausing on where ASML itself came from, because the company's own history is part of why it ended up in this position rather than a rival. ASML began as a spin-off from Philips, the Dutch electronics giant, at a time when lithography was a much simpler business dominated by a handful of competitors, most notably two Japanese companies, Nikon and Canon, both of which had deep, long-standing expertise in precision optics from their camera and imaging businesses. For years, those two companies were considered the more obvious leaders in the field. ASML's eventual advantage didn't come from starting further ahead, it came from a willingness, decades later, to commit enormous sustained investment to a technology, EUV, that for a long stretch of time looked more likely to fail commercially than to succeed. Nikon and Canon, weighing the same technological bet, made different strategic choices about how aggressively to pursue it, and by the time EUV lithography became commercially unavoidable, ASML had already accumulated a lead in the underlying engineering that neither competitor could easily close. That lead was widened further by a decision that turned out to matter enormously in hindsight. Instead of trying to develop every piece of this technology in isolation, ASML embedded itself inside a web of research partnerships with universities, national research institutes, and its own customers, treating the development of EUV less like a single company's internal project and more like a shared industry undertaking with ASML sitting at the center, coordinating it. And that leads to another underappreciated part of the story. ASML's customers didn't just wait for a finished product, they helped build it, and in some cases took direct financial stakes in ASML itself to make sure it happened. Chipmakers, including Intel, Samsung, and TSMC, invested directly in ASML's development of EUV technology. During the years when it wasn't at all clear the approach would work commercially, some of them taking equity positions in the company specifically to fund the research. This wasn't charity and it wasn't a favor. These companies needed EUV to exist in order to keep advancing their own chip technology. And no single one of them could develop the underlying machine alone. The cost, the technical risk, and the decades-long time horizon were too large even for the biggest semiconductor companies on Earth to absorb individually. So instead of competing to build their own lithography systems in-house, the industry's biggest players effectively pooled resources into ASML as a shared specialized supplier, on the understanding that a working EUV machine would benefit all of them collectively, even though they remained fierce competitors with each other in every other part of the chip business. This is a very different situation from an ordinary monopoly, and it's worth being precise about that difference, because the word monopoly tends to imply something deliberately engineered to exclude rivals. ASML's position isn't the result of blocking competitors or cornering a market through pricing power or exclusive contracts. It emerged because the underlying problem was so difficult and so expensive that the only economically rational path forward for the entire industry was to concentrate its most difficult, most specialized engineering into a single supplier, rather than duplicate that effort 3 or 4 times over at 3 or 4 times the total cost, with no guarantee that any of the parallel efforts would succeed at all. The barrier isn't legal. It's not really financial either, in the narrow sense of simply requiring enough capital to buy your way in. The barrier is the accumulated distributed expertise of an entire ecosystem. Years of trial, failure, and refinement spread across multiple companies and countries that cannot be rebuilt quickly, no matter how much money is thrown at the problem, because money can't compress the years of iterative engineering failure that had to happen first. Once EUV systems reached commercial reliability, the effect on the chip industry was immediate and significant. Chipmakers who could access these machines could keep shrinking transistors and improving performance in line with the pace the industry had come to expect from itself for half a century. Chipmakers who couldn't access this technology for financial, geopolitical, or supply reasons found themselves structurally unable to keep pace at the most advanced process nodes, regardless of how talented their own chip designers were. In other words, a company's ability to design the world's best chip stopped being the only thing that mattered. Access to the one machine capable of physically printing the chip's design onto silicon became just as important, and in some cases more important, than the design itself. This is where the story stops being purely about engineering and starts intersecting directly with global politics. Because EUV machines are so central to producing the most advanced chips, the kind used in cutting-edge computing and artificial intelligence, and increasingly in advanced military and strategic applications as well, the ability to buy or to be denied. One of these machines has become a matter of national strategic concern rather than a purely commercial transaction. Governments have placed restrictions on which countries and companies are permitted to purchase the most advanced ASML systems, treating access to this equipment in a way earlier eras reserved for advanced military hardware. The Dutch government, under pressure from allied governments, has restricted export licenses for ASML's most advanced machines to certain markets, a restriction that has direct consequences for how quickly chip makers in those markets can advance, no matter how much domestic engineering talent or capital they have available. It's important not to overstate this part of the story though, because it can distort the more fundamental point. These export controls are a political response layered on top of an underlying technical reality. They didn't create ASML's bottleneck, they exist because the bottleneck was already there. If any other company, in any other country, could build a comparable machine on a comparable timeline, export restrictions on ASML's products would simply push customers toward that alternative. The restrictions carry real weight, specifically because no such alternative currently exists at the leading edge. The bottleneck is the underlying story. The export politics are a consequence of it, not a substitute for understanding it. It's also worth being precise about where ASML's dominance actually sits within the broader chip industry, because it's easy to blur categories here in ways that overstate the company's role. ASML makes the lithography machines. It does not manufacture the chips themselves. That work is done by chip makers like TSMC, Samsung, and Intel. running these machines inside their own fabrication plants alongside hundreds of other pieces of equipment from dozens of other specialized suppliers that handle everything from depositing material onto the wafer to cutting the finished chips apart. ASML is not responsible for chip design, and it doesn't control what companies like Nvidia, Apple, or AMD choose to build with the manufacturing capacity that these machines make possible. What ASML controls is a specific, unavoidable step in the physical manufacturing process, arguably the single hardest step and the one with the fewest viable alternatives, but it sits inside a much larger chain of companies, each contributing a piece that the others depend on and none of which could function without the others. The story doesn't end with EUV itself, either, and this matters for understanding where the whole system is headed next, because the underlying physical pressure that created EUV in the first place hasn't gone away. Even EUV lithography has its own limits. The same logic that pushed the industry from older deep ultraviolet light toward EUV is now pushing engineers to refine EUV machines further still. The next step is called high-NA EUV, a more advanced version of the same underlying technology, using larger, more precisely engineered optics with a wider numerical aperture to focus the light even more tightly, enabling even smaller features to be printed onto the next generation of chips. These new systems are, unsurprisingly, even more expensive and even more mechanically demanding to build than their predecessors. A single high-NA machine costs substantially more than the standard EUV systems that came before it, and it relies on mirrors and motion systems pushed even closer to the physical limits of what precision manufacturing can achieve. Just as before, this next generation depends on the same accumulated network of specialized suppliers, refined and pushed further rather than replaced outright, which means the pattern that created ASML's position in the first place is simply repeating itself one level up, an extraordinarily hard physical problem solved only through a coordinated, multi-company effort, sustained over a very long time horizon, that competitors would need years, not months, to even begin to approach. What all of this adds up to is a company whose advantage doesn't sit in a vault, protected by a lock that a rival could eventually pick with enough time or money. It sits distributed across an entire supply chain, a set of working relationships built over decades, and a body of accumulated engineering experience that cannot be purchased, licensed, or downloaded, only built, slowly, through the same long, expensive, failure-heavy process that originally produced it. A competitor with unlimited funding still can't simply buy their way to the same position within a few years, because the thing that's actually missing isn't capital. It's time, trust between dozens of specialized partners, and the specific hard-won knowledge of exactly how to make an almost impossibly precise machine work reliably, every single day inside factories producing the chips that the rest of the modern economy, and increasingly the artificial intelligence systems reshaping it, now quietly, almost invisibly